Hello, everyone. Welcome back to the TBS Colloquia. Today, I have the great pleasure of presenting Emille Ishida. She's a research engineer at Clermont-Ferrand, and she will tell us about the Fink broker. So please, Emily, take it away.
Hi, thank you. Thank you, Priscilla. Thanks, everyone. Thank you for the invitation. Thank you for having me here. I'm going to talk to you about the Fink broker and the preparations that we are doing for the beginning of Rubin. I just wanted to, the idea here is to present to you what the broker is doing at the moment, but please keep in mind that everything that we do on Fink is on demand. So every single feature that you are seeing is there because someone asked for it. So if you think that a little bit of tweaking, or if you would like to see something different on everything that I'm going to say, it's always possible to adapt for your specific science case. Okay, so let's go. I'm going to go quickly through this because I think you are pretty aware of the data path for Rubin, which is the same that we are now using for ZTF. You have a transient that explodes in the sky. You had a difference imaging analysis. The telescope generates alert stream that goes to the brokers, and the task of the broker is to separate the stream. So use machine learning, catalog association, join streams, anything that is necessary in order to downgrade the size of the stream and separate the data to specific users that will actually do something with the data, that will actually do science with the data. So these alerts are, each one of these alerts is a little data package that gives you information about what is changing on the sky at that point. And keep in mind also that these two groups here, if you have two groups here that want to use the broker for something, these two want very different things. So the idea is to build a system that can be flexible enough to adapt for the use and the science case of each one of the users. Also keeping just a little bit on how do we get here. So for ZTF, there are a few brokers that are playing this game. Fink is one of the new brokers, meaning that we were built to work specifically to work with Rubin. So we didn't. We now work with ZTF, but the idea from the beginning, when the broker was constructed, was prepare a system to work with Rubin. So the project was funded since 2018, 2019. So it has like 5 years or something like that. And 2021, there was a selection. It was an open call. Many groups applied, and 7 brokers were selected around the world. So I have 3 in the US, 1 in Chile, and 3 in Europe. So I am going to talk about Fink, but also keep in mind that there are other brokers out there. So what is the main? I think the main thing that you have to keep in mind, because as I said, there are many brokers, and I always joke with not so much joke, but I always tell to people who are using the broker, if you go, I will show you later the Fink website. We have even a link to other brokers, and the idea is that you can find the one that is more suited for your scientific needs. The idea is not to use blindly, but also to take a look in the brokers and understand which one is more adaptable to whatever you want to do. And why this is important? Because the alert information alone is not enough. The alert will give you a light curve on difference imaging light curve, so not calibrated. Postage stamps, you are going to have a postage stamp with the template image, postage stamp with the science image, which was the image taken today, and a difference imaging, so one minus the other. And some metadata. All of these will come inside the stream, and it will be equally distributed through the 7 brokers. However, in order to get some science out of this, we will need to have developed communication protocols and involve experts in the different science cases in order to optimize what it's doing. So the idea here is actually to use all of these tools, including machine learning, to build an adaptable system that can work as a discovery machine. Because remember that if everything goes as planned, the alerts will be available shortly after detection. It's going to be on real time, and all the alerts are public. So really the scientific potential in the data is very high if we can take good care of it. So just very quickly, how do you classify alerts? So this is the same path that I showed you before, but it's in straight line now instead of a round one. So you have the telescope, you have a difference imaging analysis. This is sent to the brokers, and the brokers will separate and send different small patches of the stream to different users. So the way Fink is structured, so the Fink infrastructure is centered for ZTF in Paris-Saclay, which is in the south of Paris. For Rubin, it will be in Lyon. We have a computer center there. But the Fink team is responsible for the Fink infrastructure, for the treatment of the data. But in order for you to filter the data, you can do it with a filter, you can cross-match with a catalog that you know, or you can build a tailored science module. All of these are the responsibility of individual science teams, which are spread all over the place. So Fink now has, it started in France, but now it's like almost 80 people involved in 13 or 14 different countries. So the science teams specifically normally are interdisciplinary and international and geographically spread all over the place. For about the thing that I told you before, I think people normally ask me what is like, why would I use Fink instead of everything? To be really sincere, if you have a question that is like a cut or a simple filter, basically most of the brokers will do the same, will do the job for you with different languages and different interfaces, but they can do the job easily. The idea of Fink is that Fink was constructed to be modular in case you have a very complicated question. So what I'm going to talk to you today is how to develop a science module. A science module can be is a Python function, basically, that input an alert plus whatever data you can give us in order to input into your science module, and outputs or a Boolean, yes or no, or a probability. And then you can put a filter on top of that output. So I want to receive everything that is true from my Boolean output, or I want to receive everything with a probability or a float on a given interval value, for example. This can be done. So outputs of science modules are or scores or Booleans. And I'm going to talk to you about the early supernova classification with the sole excuse that this is what I can talk about more easily because I am a supernova person originally. But keep in mind that Fink now has a dozen different science modules or more that do different things. This is just my super biased choice of what I know how to do. So what is the problem? The case study that I'm going to talk about is supernova classification. I know some of you have already seen me talk about this many times, so hang on just a little bit more. The idea is to identify supernova which are suitable for spectroscopic follow-up. So you want them to be going up, not after peak. And you want the module to be light and to be trained and very easy to process. The problem that we all know is that in astronomy, in order to train, you need labels. In order to have labels, you need spectroscopy. And the parameter space where spectroscopic data live, like light curves, which were spectroscopically confirmed, the parameter space where they live is very different from the entire photometric sample for which you do not have a confirmation. There are many options on how to go through this, how to approach this problem. One of them is what we call transfer learning. So, okay, I do not have data. I do not have enough labels, representative labels, because remember that any machine learning application that you have has underlying the hypothesis that you have a training sample and a target sample, and then these two is representative of each other. So if you don't have that, what you can do, if you don't have that on your real data, one of the possibilities is that you do simulations. So if you have a simulator, you believe your simulator, you can simulate as many things as you want and build your classifiers on that. So this is one option. We use this with the supernova classifier, which is deep learning based classifier. I am not saying anything about this because I'm not a deep learning person. This is developed by Anais Muller in Australia, which is one of the co-PIs of Fink. In this sense, you use the simulations, you train, test, because then you have a lot of data, develop your machine learning model, and after it's done, you apply it to real data. So you are transferring knowledge from one domain to the other. This is if you wanted to use simulation, sorry. Now, if you want to use real data and labels are absurdly expensive, what you can do is to optimize the way you get labels. So you can optimize your training sample by only getting labels from things that are really important. So one way of doing this is to use something called active learning. So you start with a very small amount of labels, like 10 objects or something, for which you have labels for that. You build a machine learning model that is going to be bad because you only have 10 labels for training, but it will give you a probability. So probability of class A and class B. And then once this is done, you apply this model to the sample for which you do not have classification. And once you apply to that, you go to this sample and you pose the question, which object for which I still do not have a label would be more interesting to my model in case the label was provided, right? So in this sense, for example, if you have two classes, 1A, not 1A, what you are going to do is you are going to ask, give me the objects whose probability is closer to 50%. Because that means that object, your model doesn't know anything about that object. It's exactly on the border of your classes. You choose that object, you give it to a person. This person takes a spectra for you, or a telescope, and it takes a spectra for you. Once the label is available, you put the label back in the training sample, and then you do this again. This ensures that every time you are asking for a spectra, you are sure that that spectra will be informative to your machine learning model, right? You are not going to spend spectroscopic time on things that are already in your sample. This seems very complicated, but once you are done, it's just a machine learning model. So you run this thing a little bit, and then once you are done, you're done. You have a trained machine learning model. And this is exactly what we did. So what we did was we took the data, we built two functions actually. So you see this science module is a combination of two functions. You have one function based on the deep learning classifier and one function based on a random forest model whose algorithm is super simple, but the construction of the sample, it was more complicated. And both of them will give a score. So you see, these are two machine learning models which are absurdly intrinsic in philosophy of what they are doing. Whenever these two guys agree, meaning if this one tells you that the probability of being a 1A is higher than 5%, and this one also tells you that the probability of being a 1A is also 5% more than 0.5, this thing is sent to TNS. So we say, Fink discover early supernova candidate. And I know this name is not completely super true. Early for us is before peak, right? So you will see things that exist already, but they didn't start going down. And then once this thing, so this is automatically done. during the night. And then every time something has a probability higher than, these two probabilities are higher than 5%, this thing is sent to TNS. We have been doing this since November 2020. So just to have a little bit of these statistics here, we have reported these to TNS. And then from all of the objects that we have reported to TNS, 82% are confirmed classification as type 1A. Look at this. Let's be very careful on reading this. Okay, take this with caution. Because first, we know that TNS is very supernova biased. We know type 20s are very bright. And on top of everything, there's still a person here. There is still a person that has to look at the light curve of the candidate and say, I am going to take a spectra of this. And this we are not modeling. So although these numbers are very easy to interpret, because if you go to the paper, the tests that we made during the training were exactly 80%. So like it's very easy to say, I told you so, but keep in mind that modeling this is more complicated. This is, for me, I understand this as an indication that we are going in the right direction. However, in order for this to be, in order for developing this, what we did was we took past data from ZTF. So you see that this was put in place in 2020. So there was a little bit of ZTF data already. So we took data from ZTF with labels from TNS and other places that we could find in order to do the loop. So the loop was not real in the sense that the labels already existed because it was on catalog data. And we every time the algorithm made a question, we kind of mimic the fact that someone had taken a spectra, but this was still super controlled. What is important to remember here is that this is a random forest model trained in 330 alerts and has been giving consistently 82% purity since 2020. Just because you actually choose the training sample, but it was still not the real thing, right? The real thing is when you choose an object and then you get someone to take a spectra for you, and then once the spectra is done, you put it back. And why I call this is the real problem, because here you have observation in place. So sometimes the algorithm will ask you an object and the object is in the wrong place. It's not visible. It's there is clouds that day and you cannot change it. And the label will come to you a few days after. So this is much more complicated. This is a paper also by Anais where we did all of this using the ANU 2.3 meter telescope in Australia. And what you are seeing here is the accuracy of the classification over the number of spectra. The right is easier to see. So this is the accuracy given the number of spectra. The blue ones, it's what happened if you take only labels for the training sample for the objects that were queried. And in the orange one, you see what happens when you just take everything that is available on TNS. So having more objects, having more spectra, not necessarily will give you a better information, because at some point you are going to start biasing your data to the direction of the spectra that are being taken, which is not the goal of your task. So what I want you to remember from all this, there are many different strategies of active learning. Okay, I told you the most simple one, which is called pool-based active learning, and it's only one possible strategy. There are others, and I think they should all be tested. By definition, the output of all science modules in Fink are public available. So the science modules are developed by different teams, but just because you develop your science module does not mean that it's not public to everyone. The probabilities of everything is public to everyone. This means that in building your own module, you can use probabilities for other people, from models for other people. For Rubin, I told you that there is this problem that the initial thing that we did was not in real time. The ANU, the Australian result that I just mentioned, it was real in the sense that the data was really taken on the go while we asked for it, but there was still a person. So we still had to press the button to train the model and to report and everything. For Rubin, we would very much like to have all of this automatized. So we have a wish list. As soon as any object of our list is published in some public forum, we grab that label, put back onto the sample automatically, and then I don't have to do anything and we can sleep. That is the main goal of this. And this strategy, I told you about Japanese supernova, but this would work well for any well-defined classes. So any classes that well-defined, I know, like we have been studying supernova 1A for a very long time, so we more or less know how they look like. And you know what you're looking for. You wanna find them because you wanna do other things with them. In this sense, you can probably build an algorithm to classify them because your class is well-defined. Once you are done, if I have time, I just wanted to show you a little bit what happens once your model is integrated. So once your model is done, you upload it to the broker, and what happens is you can come here. So this is the Fink science portal. This is a search bar that you can do. You can find anything you want. So if, for example, you can choose, I don't know, NGC something, it should find some object for you. You can find, there is an asteroid called Julian Peloton, which you can also, you can also get things for that. You can also come here and it will give you the alerts associated to that object. So since this is an asteroid, you can come on a sky map and you will see the projection of the thing inside on the sphere. And then you have the identification of each one of the alerts. But we were talking about supernovae. So what do I do if we suppose that you did you become your model, and then you can have here, and then your class will be identified here. You can just come and say, okay, I want early supernova 1A candidate. You push it, and it will give you the 100. In this case, the 100 early supernova candidates.
I'm sorry, Emily.
Yeah.
We are still seeing the sky.
You're still
picture.
seeing the sky?
Yes. So if you were doing a search on supernova, we didn't see that.
Ah, okay. Do you see my slides now?
No.
I'll try again.
Okay.
Sorry, this is probably my internet. Let's try again. Do you see?
It's sharing. I guess it's loading because
Oh gosh, I'm
it's
sorry.
only, no, don't worry. It's okay. No, it's just the black screen.
It was working.
It was working, yes.
Oh gosh, I am so sorry.
No, it's okay.
Okay, everything is black now?
Yes.
Okay, let me try again, just a moment. So I will do something like, okay, let me try again. So do you see my slides now?
Yes. Now we see your slide.
Yes.
Yes.
Okay.
Perfect.
Now you see the portal.
Yes. So
Okay.
if you want to show again the search.
Yes.
Yes. Thank
So
you.
I'm sorry. Ping me again if this happens. So I was saying that you develop your science module. So you have this science, this early supernova, for example, but any other class, you can come here and then you will find the list of classes that we have. So these are all science modules within Think. We also have some cross-match, for example, with catalogs. So at least TNS and Sinbad, you can find it here. But for now on, let's say that you built your model, you upload it to the broker, and then you can come here and this will give you the list of early supernova candidates. I told you that early was a little bit forced because it should be called before peak. And you see that all of these light curves, they are not falling, but they are not also what you would call early, right? And this was a choice. When developing the model, we have to choose between having a very high purity and giving the classification a little bit later, or having a lower purity in the final sample and providing the classification earlier. And we decided by the first. So these are all how things are going to go. But if you come here, for example, you come to the object page. So this is the page where you are going to find a lot of information about this object. You can check, these are the postage stamps that I said, the science image, the template image, and the difference. And here you have links to many other things, other brokers, neighborhood, where you can cross-match with TNS, SIMBA, SNAD, many other stuff that allows you to have a better idea of these objects. If this object exists in data releases, you can also get data releases by clicking here. This one you will not have because it's 25, so you're not gonna probably not gonna get data from data releases. But if it was a longer object, you would find data in data releases. You can get coordinates, download the data, and things like that. So this is if you know the class, right? So you know the class and you want to classify things there. All of this is possible. Now, what happens if you do not know the class, or you want to find anomalies, for example? So we also have an anomaly detection module. This work is led by Maria Prushinskaya. I think she talked to you recently about some other projects, but the idea would be, I told you that a science module can be a function, right? Any function. In this case, it was an isolation forest. It was a machine learning model built from an isolation forest that produces anomaly scores. Producing anomaly scores, this was the first night that we used the anomaly score on Fink data. I am not a stellar person, but I was told that this was the object that we found in the first night that we put the anomaly there, and there was not so many examples of this object.
I'm sorry again. Can I also interrupt again?
Yeah.
Can you minimize the box with that box? Yes, perfect. So we can see the name of the star. Yes,
Yeah,
thank you.
yeah. So,
thank you.
So the point is, this model was a very simple anomaly detection module. So it was an isolation forest using features from the light curve package, which was also developed by the SNAT team. We used features from the light curve package, and we applied a isolation forest on it. And then we put it in the broker, and this was the first night. This was the first object that was flagged. For me, the most interesting thing about this was, first, that the machine learning model was very simple, and second, that it was our opportunity to start talking with other actors in the community to get follow-up. So we get follow-up from South Africa, Russia, Spain, Italy, and this was super nice because this was the first opportunity that we had to start a conversation and start keeping things in place to when Rubin actually is gonna start. All these conversations are still ongoing. So but there are, I didn't told you, I should have told this. There are many ways that you can receive the data. One way that you can receive the data is through a Telegram bot. So your science module will add those tags in the portal, but we have also a few Telegram bots that you can use to receive your data. So we have the anomaly detection bot, and the idea in the future is to do an active learning for anomaly detection, similar to what I told you before about the classification. So the idea would be that you would have an initial isolation forest model or anomaly detection model, whatever you want. You go to every night we post the 10 highest objects with highest anomaly score. So from these 10 objects with higher anomaly score, it's Telegram, so you can react, right? You can say, yeah, I like it, I didn't like it. And this thing automatically is recorded. And once in a while, we upload, we retrain the model based on the reactions of people. So although in the beginning is not very good, the idea is that reactions of people help to upgrade the model bit by bit. And the idea is that even if you don't know, if you don't have a mathematical description of whatever you're looking for, but you see an example of something that you like, you can just react, and this information is put into the system. So you can try that. Nowadays, it's not so. We are writing the paper to describe all of these systems. Nowadays, the training is not super. The schedule of the training is not absurdly constant. So once every 1 or 2 weeks we said this, but the idea is that as we move forward and the system is being tested by many people, once we have to a more stable version, the training and the uploading will be automatic also. So we don't need to worry about that too. So what do I want to tell you with all this? I want to tell you that all of these big data, and obviously there is super complicated issues that will have to be addressed. But the main important thing is that we talk to the people in the end of the line who are going to do science. And this is a strategy that we have been doing in Fink for a very long time, since the beginning. So first you go to the expert and you ask them, what do you want to see? And you build your system around it. All Fink science modules are built like that. And in order for that to happen, you need to meet people. You have to talk to them in person and understand what do they want, what are the problems, how this can be solved, and how we can collaborate together to make everything super clear from the start. If I develop the most amazing machine learning model possible and I arrive to the expert and say, here is the perfect model, please use it, they won't. They won't because they will not understand and they will not believe me, and they are completely right. Right. So since the beginning, we are working with the experts, with the observers, trying to build this thing. And these conversations are super important. So I told you now that Fink has almost more than around 80 people in 14 different countries. And this is a few of the meetings. We try to make these meetings as frequent as possible in different parts of the world so we can actually go there and talk to people. As a result, we have already organized I say offices, but I mean people with local funding organized and actually working on Fink data in Australia, in Brazil, and in France officially, and we are working towards other centers. So what do I want you to remember from all this? That brokers are, first of all, discovery machines. You are going to take LSST, Vera Rubin, which is the largest camera ever built. You are going to point somewhere in the universe that nobody has ever pointed such a big camera before. You have to see something new, but you will not find it in the middle of the data if you don't know exactly how to deal with data on that scale for your specific science case. Easily adaptable systems highly increase the probability of realization of potential scientific data. And the active anomaly detection that I mentioned is one possible strategy. There are others, and they should not be tested. It is, moreover, in this realm of discovery, of trying to find things that we are not sure yet that they are there, it is absurdly important to have strategies that allow users to search for things, even when they do not have a mathematical description in mind. Because at this point, it is quite possible to, if you have very well an idea of what your class is, you just want to find more of the same. This is pretty easy, but it is possible to be implemented. but you should allow users to do it even when they do not have a scientific question in mind. So all of this that I have been telling you is for ZTF. What about Rubin? So we are working in the preparations in many different stages for preparing for Rubin. OR5, which is operation rehearsal, is currently on the way this week. And these are like massive tests where we are training the communication protocols between project and the brokers. So the data that is being transmitted is toy data, like it's just numbers, they don't have any scientific meaning, but we want to pass the data through all of the science, well, the main science modules, in order to make sure that in terms of computer performance and the throughput, we will be able to deal with Rubin data. So this is currently undergoing. One thing that we learned very recently, no, for a long time already, is that moving from ZTF to Rubin, as much as we would like to be smooth, will not. Rubin is going to be much more complex in not only on data volume, but in the complexity of the data that is coming. There is going to be 6 filters, it's going to be deeper, there's going to be a lot of other problems. And we are tackling this the best that we can at the moment, which is using simulations. So I think Bernardo is going to talk to you eventually about a few of the studies that we are doing with simulated data, which is super important. It's where we are going to start, because from Rubin, since there is no real data available, the only thing that the maximum that we can do is really use simulations for that. In the beginning of what should be our expectations in the beginning of Rubin? So the first year of alerts will not be nice. We are going to start receiving alerts since the first light of LSST, but it will not. The first alerts will be very difficult to be used because we don't have templates, right? So remember that alerts are based on difference imaging. The difference imaging depends on templates, and it takes some time for you to get reliable and good templates. But it is very good to start thinking about the data and to start getting some intuition about how to deal with the data, because building that intuition will take time. Fink operations will not change. This is a question that I get a lot. If the how Fink operates will change under Rubin, it will not. Each science module is developed by a different dependent science team, and the output of all science modules are available to everyone. The core development of Fink is done upon demand, meaning, as I told you in the beginning, every single button that you see on Fink is there because someone asked for it. So we only develop we can develop a few things for specific science modules, but we are only going to do that if we know that there is a science case on the other side. So if you have an idea, please talk to us, and please talk to us before Rubin starts, because afterwards things are going to be much more messy. I am going to leave here with you a few of the links, how you can access the data. I talked about the science portal, but we also have live streams. We have the data transfer module. If you just want to do book downloads of alert data, you can do it from there. And I think that's what I had to talk to you. Thank you very much.
Thank you so much, Emily. This is great. Yeah, I hope a lot of people contact you, and so we have many useful science kits for the brokers. So thank you so much.